All right, let's continue with liquids. So what is the biggest difference between a solid and a liquid? So they have some properties in common, but there's some definitely noticeable differences. Like in a solid, the particles of a liquid are touching each other. So they're close together, which means they're held together by relatively strong attractive forces. So the difference is here. The particles in a liquid as opposed to a solid can still move past one another. Remember, the particles of a solid are held tightly together in fixed positions. They can't move around relative to one another. For liquids, the particles can move around relative to one another. So held together by somewhat strong attractive forces, but the attractive forces between the particles of a liquid are weaker than the attractive forces between the particles of a solid. It says in letter B, the particles do not possess enough kinetic energy to separate from one another. So this implies, I guess, if you add enough kinetic energy, that you could cause the particles of a liquid to separate from one another. We'll see that later. Because the particles cannot separate from one another, liquids get much more dense than gases. Remember, particles of a gas far apart from each other occupy a relatively large volume for a small mass, leading to low densities. Liquids, particles are close together, going to result in a higher density than gases, but usually lower density than solids. Both gases and liquids flow, and thus are called fluids. So you'll learn about fluid dynamics in physics, properties of liquids and gases. All right, evaporation. Let's start off with a definition, and I'm not talking about what's in the notes there. What do you think of when you think of evaporation? Like freezing and melting, evaporation is a physical change. It is a phase change. So what does that mean? Evaporation is a process where a liquid turns into a gas. Now be careful with that though, because there's another word that means the same thing. So let's take a look at this definition here. The conversion of a liquid to a gas, here's the important part, at a temperature below its boiling point. True or false? All liquids evaporate. All liquids can evaporate. True or false? Pause the video. Tell me now. All right, that is true. All liquids evaporate all the time. And so liquid turns into a gas at a temperature below its boiling point. We can see that when we have, say, a puddle of water outside on the sidewalk after a rainy day. If the sun comes out and it gets warm enough, that puddle will disappear. It'll dry up because the water evaporates. Never do we see that water boil, though, but it turns into a gas. Speaking of heat, what happens to that puddle on a hot day versus on a cold day? On a cold day, that puddle takes a long time for it to dry up and disappear. On a hot day, it disappears pretty quick. So liquids evaporate faster when heated because a greater proportion of the particles possess enough kinetic energy to break free into the gas phase. So if you take a look on page 422, going back to our kinetic energy distribution curve, if more particles have enough kinetic energy to break free of their attractive forces, then that substance is going to evaporate faster. So evaporation, another property is it usually occurs to the particles on the surface. The particles on the surface exhibit less attraction to other particles because they're only held by the particles next to them and below them, versus a particle, say, in the middle of a liquid, which is held by other particles all around it. And because of that, the particles on the surface have, on average, a higher kinetic energy than the particles in the middle. And if they get enough kinetic energy, if they get moving fast enough, they can break free of their attractive forces and become a gas. Let's say you have a closed container of some liquid. Here's what happens. In a closed container, a point will be reached where the rate, how fast, the rate of evaporation equals the rate of condensation. We can see that at the top of page 423. Take a beaker of water, cover it, Initially, the water will evaporate, but as the water evaporates, it makes water vapor, it's called, water in the gaseous state. And those water molecules start moving around, and some of them collide with the water, the liquid, and reform the liquid state. Eventually, what happens is for each particle that turns from liquid to gas, you have a particle that turns from gas to liquid. This situation where you have two opposing processes, in this case evaporation and condensation if you recall is changing from a gas to a liquid, two opposing processes are occurring at the same rate is known as dynamic equilibrium. Is we can write one equation showing both processes that are occurring inside that beaker. Recall that evaporation is endothermic, right? It takes energy to turn a liquid into a gas. Better yet, it takes energy to break attractive forces. Energy is released when attractive forces form. So we're going to put the heat term on the left side of the equation, and I'm going to use this double or two-way arrow, I call it. And so we can read this equation from in either direction. So reading it from left to right is the equation for evaporation, and reading the equation from right to left is the equation for condensation. We have this two-way arrow here indicating that both processes are occurring at the same rate. All right, be careful this next one. Boiling. What do you think of when you see that word boiling? What does boiling mean? Again, please don't read the definition in the notes. What does boiling mean? Pause the video. Boiling is a process where a liquid turns into a gas. I think we already used that one though for evaporation. So what is the difference between evaporation and boiling? Well, technically, here is the definition of boiling. A liquid will boil when its vapor pressure, it's called. Vapor meaning the gas particles that result from that substance evaporating. When the vapor pressure of a liquid is equal to the atmospheric pressure. Take a look on page 428. So think of the gas that is being produced inside the liquid as pushing up against the air, and the air is pushing down on the liquid. When those two forces are the same, the liquid will boil. What else do you think of with boiling? Some of you might say hot. Liquids that are boiling are hot. I challenge that thinking. Have you ever seen liquid nitrogen? Liquid nitrogen boils right in front of your eyes. And guess what temperature that substance is when it's boiling? Nearly negative 200 degrees Celsius. So be careful. Boiling doesn't always mean hot. How do you boil water? Well, we need to do something to the vapor pressure. We need to increase the vapor pressure of the water because water, say at room temperature, has a vapor pressure of about 20 something torr. Well, in order for that liquid to boil, we need to increase its pressure to, say, 760 torr, same as atmospheric pressure. It won't boil until the vapor pressure is the same as the atmospheric pressure. So what is boiling point? Boiling point is the temperature at which a liquid boils. The temperature at which a liquid's vapor pressure is equal to the atmospheric pressure, or the pressure that's pushing down on that liquid. How's air pressure at high altitudes compared to air pressure at sea level? So here in Placentia, we're about sea level. Air pressure is about 760 torr. As you go up in altitude, and so as you're driving up, say, to Big Bear Mountain, the air is, we say, thinner. It's actually less dense. There's less air particles at higher altitudes, and so the pressure is lower at higher altitudes. Now, what effect does this have on, say, the time it takes to cook mac and cheese? Suppose you went up to the mountains, you want to cook some mac and cheese. So you take some water, put it in a pot, put it on the stove, and heat it up. Well, what's going to happen? the vapor pressure of the liquid is going to equal the lower atmospheric pressure at a lower temperature. So water boils at a lower temperature at higher altitudes. So what effect does that have on the time it takes to cook your food? It's going to take more time. So instead of cooking your mac and cheese, oh, before I continue, let me ask you this. What is the boiling point of water? Go ahead and pause the video and answer that question. All right, what did you get? Did you say 100 degrees Celsius? Again, I'm going to challenge that. I'm going to say sometimes. Sometimes water boils at 100 degrees Celsius. Let's go back to this example. So at a higher altitude, the air pressure is lower. The water is going to boil at a lower temperature. So instead of cooking your mac and cheese at 100 degrees Celsius, you're cooking at, say, 80 something or maybe 90 degrees Celsius, depending how high up in altitude you are. So it's going to take longer to cook your food. Now, a lot of times students say, oh, your food will cook faster. No, I don't think so. So though the water will boil faster or get to that point faster, it's going to be at a lower temperature. So people use this idea to help them develop items to sell, like a pressure cooker. These Instapots are super popular now. How does this work? So you take a pot, put some water in it, put the lid on. That lid seals. It's not like a regular pot where you just set the lid on top. The lid seals, and as the temperature inside increases, so does the pressure. And as the pressure inside increases, so does the boiling point of the water. And so instead of cooking your food at 100 degrees Celsius, you're cooking it at a higher temperature. The water inside there can increase to above 100 degrees Celsius. If I get a chance, I will show you that I can boil water with an ice cube. I'll also show you that I can boil warm water, not hot, warm water. So let's go back to a question I asked. What is the boiling point of water? It depends. What does it depend on? It depends on that. So the boiling point of water or any substance is variable, depends on the atmospheric pressure. So now for those of you that said 100 degrees Celsius, you're partly right. 100 degrees Celsius happens to be what's called the normal boiling point. Normal boiling point refers to the temperature at which boiling occurs when the atmospheric pressure is 1 atmosphere. If the pressure is not 1 atmosphere, the liquid will boil at a different temperature. For water, it's going to boil at some other temperature besides 100 degrees Celsius. Take a look on page 430. There's a table. Mount Everest, what's the elevation there? 26,000 and something feet above sea level. Look at that, 76.5 degrees Celsius. Not very hot at all. Water down here at sea level boils at 100. San Francisco, New York, Madison, Wisconsin, about sea level, 100 degrees Celsius. Death Valley, a little below sea level. Atmospheric pressure, probably a little more than 1 atmosphere or 760 torr. So water boils at higher than 100 degrees Celsius. Letter F, very interesting as well. The temperature of a boiling liquid as it is boiling never increases. How about this? Sometimes I ask this as a question. What happens to the temperature of water the longer you heat it? The longer you heat water, what its temperature? Nothing. It gets to its boiling point. Let's say it's 1 atmosphere pressure. It's going to get to 100 and stay there. So why do you have to keep the fire on? Well, the fire then, that energy is used to break the attractive forces between the liquid particles, the water molecules. It's not used to heat up the liquid, not anymore. All right, take a look on page 429, and we'll use that one first, and then we'll use this as an example. So we're given a graph of vapor pressure versus temperature. The question it asks in your notes, which substance exhibits greater intermolecular forces, and more importantly, why? So remember, boiling has to do with separating particles, separating liquid into gas. You're breaking attractive forces. And so boiling point is related to the strength of the attractive forces between the particles. So which one of those substances that's listed there in the book, CHCl3, CCl4, or H2O, has the lowest boiling point? Well, even let's go with lowest normal boiling point. Water's normal boiling point, 100 degrees Celsius. Carbon tetrachloride's boiling point, what is that? Somewhere between 70 and 80. So about 76, 77, maybe 76 we'll go with, degrees Celsius. Trichloromethane, CHCl3, has a normal boiling point of about 60. So again, answer the question. Which substance exhibits greater intermolecular forces of those three? It must be water. So the stronger the attractive forces, the higher the temperature must be in order for that substance to boil. How about here? Same thing. We got three different substances: pentane, tetrachloromethane, that's CCl3, and water. We see normal boiling point for water, 100 degrees Celsius, tetrachloromethane, 76.5, pentane, 36.1. So again, we see that these are vapor pressures here, right? So notice the relationship between temperature and vapor pressure. And then notice the relationship between vapor pressure and intermolecular forces. Water has the strongest intermolecular forces. Thus, it has the lowest vapor pressure at a given temperature, right? So let's say 40 degrees Celsius. At 40 degrees Celsius, the vapor pressure of water is right there, about 100. At 40 degrees Celsius, the vapor pressure of tetrachloromethane is about 200. And at 40 degrees Celsius, the vapor pressure of pentane is about, say, I don't know, 740, 750 torr. So make sure you know the relationship between strength of attractive forces and vapor pressure and boiling points, strength of attractive forces, and boiling point. Remind me too, we'll do some more examples in class. Actually, I don't know if we'll get to that, so let's do that now. I'm going to give you a couple substances. You tell me which one has a higher boiling point: methane or carbon tetrafluoride. So with this, we need to know what type of attractive forces, intermolecular forces, they exhibit. And whichever one has stronger intermolecular forces will have the higher boiling point. So go ahead and pause the video and answer this question now. Hopefully you drew the Lewis structures for these to see what type of intermolecular forces they exhibit. Both of these molecules are nonpolar, so they both exhibit dispersion forces only. So there's a question just like this on the test. So which has stronger dispersion forces? Well, CF4 is made up of larger atoms, thus has a larger electron cloud, thus has higher dispersion forces, and will have then a higher boiling point. All right, how about these two? Same question, go ahead and pause the video. So in this case, both molecules are polar. Water exhibits hydrogen bonding. H2S exhibits dipole-dipole forces. Of the two, which is stronger? Hydrogen bonding is stronger than dipole-dipole forces. Even though H2S has a little bit higher dispersion forces, I'm still going to go with water. Stronger attractive forces, higher boiling point. How about these two? By the way, what state of matter is bromine at room temperature? And what state of matter is iodine at room temperature? All right, go ahead and answer this question, and then I'll further explain why. Both of these molecules are nonpolar, both exhibit dispersion forces. So same as the first example there, I2 is made up of larger atoms, has a larger electron cloud, has stronger dispersion forces. That is why iodine is a solid at room temperature and bromine is a liquid. And that is why chlorine is a gas. So chlorine has dispersion forces as well that are weaker than bromine's dispersion forces. Bromine's dispersion forces are strong enough to hold those molecules together in a liquid. Iodine's dispersion forces are strong enough to hold those particles together in a solid. So iodine has a higher boiling point. Next. A little bit more complex. So see if you can draw actually I'll help you with the structural formulas for these. So there's the structural formula for ethanol, it's called, ethanol. And there's the Lewis structure for ethanol. Go ahead and answer the question, pause now. Now here is a polar molecule. It exhibits dipole-dipole forces. Ethanol, also a polar molecule. It exhibits hydrogen bonding. Hydrogen bonding stronger than dipole-dipole forces. Ethanol has a higher boiling point than ethanol. All right, last section for today, sublimation, also a phase change, process of a solid converting directly into a gas. Not a very common process at all. An example that comes to mind is dry ice, solid carbon dioxide, sublimes. It's a pretty fun substance to play with. Another one is, have you seen those air fresheners that look like a cone? And they have a solid substance inside them, and then you can smell it because that solid sublimes. I think they're called like renuzits or something like that. Cone-shaped air fresheners. All right, in summary, page 431, table 17.3. Take a look there. Very important information, just summarizing some of the stuff we talked about. All right, next time we'll talk about phase diagrams. Thanks.